The title of my presentation is Column Consolidation Testing of OSN Tailings. First of all, I would like to introduce my co-authors, Ryan Spirley from SRC, Jamie Khan and Alison Gozal from Total. The outlines of my presentation include the background, objectives, experimental method and materials, a case example of column consolidation, results and discussions, conclusions, and future work. This project lasts about 3 years, and it was motivated by ERCB Directive 74, which requires deposit to reach 5 kPa 1 year after deposition. And there's a wide range of predict consolidation rates and shale strengths for a particular deposit. And for Total, they would like to know what will be the consolidation behavior for their base TT and the TT with change process or change conditions. So the objectives include to develop a test method to combine gamma density scan and pore pressure measurements. And many of you in the audience may be aware that SRC has a pipe flow model, and traversing gamma densitometer is a technology developed in SRC in-house, and to determine the size, the solid size and size distributions in the pipeline. And in most cases, it's horizontal. And in this project, we just try to find a new applications for this technology instead of have a traversing for the horizontal pipeline, and we have the vertical traversing. And so after that, we'll be able to construction of consolidation profiles and evaluate impact of process conditions on oil sands tailings consolidation behavior. And finally, to provide the data for further development and modeling. So experimental method and materials, we have a thickener. This thickener is acquired from FL Smith and capable of produce 2.5 liters per minute. The size was chosen that we can produce fresh TT within a day. Then we can load that fresh TT into column as soon as possible. So there's no gap between the times. Keep it fresh as fresh as possible. Columns 2.7 meters high and 0.6 meters in diameter. And so we have a number for indoor conditions and a number for outdoor conditions for mainly for freeze and thaw. Not included in the outdoor picture is we have another 5 columns. It's fully insulated to simulate one-dimensional freeze and thaw in the field. And because the limitation of the space of the paper and also time, I didn't include that data. Materials, thickener feed, as we produce the thickener underflow in-house. So thickener feed is from Canadian Natural. The reason we choose Canadian Natural is the lease between Canadian Natural and Total is side by side. So the property of the feed is most close to that Total's lease, although Total don't have production yet. And so when we receive the material from CNIL and we adjusted for sign-on ratio, and also the fresh TT produced from the thickener control the total solids concentration at 50%, and sign-on ratio about 0.8. That's Total's focal base case tailings. And we also, for number of tests, we adjust the composition of feed property by adding additives or change either change the rheology or change other conditions, which will be discussed in a minute. Column consolidation tests last about 12 to 18 months. I'm not going to go through the whole table here, and which is in the paper, in the proceedings. Altogether we have 18 columns, only 13 of them discussed in this paper, and I choose one to just illustrate the analysis for consolidation behavior, and we apply this method for every one of the column. And first of all, on the graph on the left, it is the gamma densitometer concentration distribution. The vertical red line represents the average feed concentration, and so this is the concentration distribution as a function of consolidation time. As you can see, the fast settling for this particular condition of the feed, the fast settling and water release within the initial 33 days. So you can see, so there's a green line at the second line, and so you can also see reach equilibrium about 120 days. Second graph is the pore pressure, the total pore pressure, and so as the pore pressure indicates, the pore pressure consolidation time, and the pore pressure is the fluid pressure at any height, any time. So as the consolidation progress, at the beginning of, as soon as you load this, the solids is fully suspended. There's no grain-to-grain contact. So as the consolidation progress and the solids start to settle, and the weight of some of the solids and transform to the bottom instead of the fluid around. So you can see as the consolidation progress, the pore pressure getting less and less. So this is one way to analyze the consolidation pattern for this particular feed. Another way to analyze the consolidation behavior is the effective stress. Effective stress is the difference between the total stress or total weight above at any point, and the difference between the total stress and the pore pressure. Again, for the same reason, as the consolidation progress and part of the weight transform to the bottom of the column instead of to the fluid. So you can see the difference getting bigger and bigger. So this is another way to analyze the consolidation behavior. So in this graph, and we have the traversing gamma density scan comes into play. Without the gamma density, it's harder to analyze the weight at each layer and the weight above, and you have to take samples and so on and so forth. It's not that accurate. With the traversing gamma scan, we are able to analyze, get the data, the scan of the concentration concentration at each layer, the same concentration as the pore pressure, so we compare directly to them. And another way is the compressibility. Compressibility is the void ratio as a function of the effective stress. And you can see as we load 11 days after loading, the compressibility is still very high over there. And so as the consolidation progress, and this value getting lower and lower until it reaches equilibrium about 125 days. And finally, there's the shear strength, and you can see that it is progressing against versus the consolidation time, and B is the bottom half meter at the column bottom exceed 5 kPa after 1 year. We apply this analysis to each and every one of the columns. And we have those following discussions. For indoor consolidation columns, the base case, to tell us the base case, is about 52% total solids concentration, center fire ratio 0.8. It reached for the indoor undrained no evaporation conditions. It's reached a 30% volume reduction and consolidated to 67%. And the average strength reached 2.4 kPa. For other conditions, such as the low feed yield stress, TT produced from aged feed or lower concentrations, those conditions achieved 41% volume reduction and consolidated to 65 to 70% average concentration, and the strength reached about 4 kPa. And as you can see, the volume reduction rate is slightly, it's different, but at the end, total solids concentration is very close. We also conduct a base case, and for base case, we are not sure one test is enough. So we have a second duplicated test with exactly the same condition and put it into a different column, and which reach very, very close results, and that itself is validate the method. And also Total requests to have 1%, 2%, 3% of the fly ash additions. The purpose of the fly ash addition is to reach a certain target of the shale strength in a very short time. And we'll see what happened for volume reduction wise after 1 year. And it's all, the volume reduction is for 1, 2, and 3% of the fly ash addition, or below the base case, which is 0 fly ash addition. So that means fly ash prevented fast water release, and such that prolonged the consolidation process. And after freeze and thaw outside, outdoors, and 3% fly ash addition reach the same or very similar volume reduction and solid consolidation concentration. The top two lines over there is the freeze-thaw condition, and one has a 3% fly ash, the other one is 0. That means freeze and thaw override the benefit from the 3% fly ash. So there's almost no benefit for the fly ash. So as I say, fly ash, the purpose of the fly ash is to reach a certain target of shale strength in a limited time, such as you reach a 5 kPa within 1 year. And so we also measured the shale strength after 1 year, indoor and outdoor. And for outdoor, 0% or 3%, and the 3% fly ash addition has a 3 to 5 kPa higher shale strength than the 0 base case 0% fly ash. However, both of them exceed 5 kPa. So, but however, for indoor fly ash addition, none of them exceed 5 kPa. And also we touch base on the freeze and thaw. Again, not included is there's 5 columns, and we recorded the temperature from October to the next year, June, and continuously record the temperature and have a thin lift versus a thick lift. A thin lift from 20, 30, and 40 centimeters. A thick lift is a 2.5 meter thick lift, fully insulated, one-dimensional freeze and thaw. However, it's not included, but the data included here show you that base case TT achieved 40% reduction after freeze and thaw, and concentrated to 72% after the first freeze and thaw. This data is very close to Dr. Siegel's observation back to '92. And the low yield stress, we showed the base case, remember that is 20 to 30 Pascal. That's a mimic, you transported the fresh TT from the thickener to the DDA, then you reach the end destination yield stress around 20 to 30, And we have one condition here is shear further, is oversheared, reach 4 to 5 Pascal, and that feed achieve quick volume reduction even before the freeze and thaw season start. However, interesting enough, the end concentration is the same. So even though you gain a very quick initial reduction, but at the end, the consolidation is to a same or very similar concentration. And also look at the second band over there. It's the orange band over there. The second freeze and thaw had a much less consolidation gain due to the structure hardening. So between that, some of the columns still have the drying. So the structure is very hard. So almost no benefit for the second freeze and thaw. All the gain, majority of the gain is right after the first cycle of a freeze and thaw. Okay. Conclusions, and indoor base case TT, which is a total solids concentration is 53, sanifying ratio 0.77, achieved 30.7 volume reduction, consolidated to 67%, and average deposit strength reached 2.4 kPa. 1-3% fly ash added TT indoors, less volume reduction than base case. The more you adding, the much less volume reduction compared with the base TT. Fly ash addition prevent faster water release and prolong the consolidation process. Small increase in deposit strength, but it's not benefit enough that it will exceed 5 kPa under the indoor and undrained conditions. And well-shared feed had a faster settling and a quicker water release even before the first freeze and thaw cycle started. For outdoor base case TTs, achieved 40% volume reduction and consolidated to 73% total solids concentration. Majority of the consolidation achieved almost immediately after first cycle of freeze and thaw. After one cycle of freeze and thaw, deposit strength well above 5 kPa. Although 3% fly ash addition achieved 3 to 5 kPa higher strength than the base case TT. However, freeze thaw speed up consolidation process by promoting fast water release and volume reduction. On average, one cycle freeze thaw reduced up to 40% feed volume reduction and increased the deposit solids concentration by almost 40%. I think that data is also agree with Dr. Siegel's observations. Impact of a second freeze and thaw on same deposit limit if the first freeze and thaw and summer drying effective. Future work, field validation test with increased deposit thickness, so you will have the more vertical stress. And we also will include the natural evaporation and the freeze thaw on oil sand tailing consolidation. So basically is enlarge the scale. The combination of a traversing gamma density scan and lateral pore pressure measurement is a powerful tool to examine tailings consolidation behavior and the further development of this technology and apply to larger scale tailings consolidation test. Thank you very much for your attention.